Leandro.
Yes, hello. So our project is steady.
No, the slides aren't moving,
Oh,
or are they?
sorry. There you go.
So go to the Meet the Team. All right, so I'm Charles Reiser. I'm an electrical engineering student.
I am Leandro Tamares. I'm an electrical engineering student as well.
I believe we are missing our third member, or is he here?
I see a Nick.
Sorry about that.
Okay, so my name is Anik Rashid. I'm a computer engineer, and basically my field is that I'm a experienced backend developer, and I pretty much am like a self-hoster of like a bunch of services I put out there.
So our project motivation is that we wanted to be able to create a tool that would have some kind of societal impact. And we mainly noticed that there's not a lot of technical solutions when it comes to the field of medicine, especially with the treatment of Parkinson's. And we know this personally because we have someone that we know in our lives that suffers from hand tremors, and there's not really a lot of treatments right now uh, for Parkinson's disease. So when it comes to project selection, we wanted to first obviously create some kind of stabilization tool, and we wanted to focus on three things, and that would be price, cost, portability, and modularity. And obviously, we had to compare it to two different other projects that currently exist, and that would be the Gyro Glove and the Steady One. And one of them, the Gyro Glove, uses gyroscopes in order to stabilize the hand, whereas Steady One utilizes nerve simulation. Leandro, you're muted.
So this is ranking us our alternative approaches. We have, this is a picture of the steady one to the left and the gyroscope to the right. So ranking our hierarchy process, we have purchase costs, operation costs, safety, and design. Clearly, if you look at the weights, the design has a higher weight than all of them. Following is the safety mechanics. After that is going to be the purchase cost and then operation cost. So this is our breakdown of our compactability and user friendly. Currently, we're going to have more weight towards the compactability over the user friendly. In comparison to the design rating on each of the alternatives, we see that Gyro Glove has a higher rating in compared to both of the techniques. So for compactability rating, we see the stable hand, which is our product, has a higher rating than both products. And in user-friendly rating, we also see a increase of rating in the stable hand. Project selection. So we see that this is a safety rating. We see that the Gyro Glove has a higher rating in safety. So our decision matrix. So each this is our marketing requirements. We have purchase cost, design, and safety. So to the right of that is the weight of each one. So product cost is going to be 0.3, design 0.17, and safety is 0.4. And at the bottom we have the scores of all the three products: steady one 0.16, gyro 0.36, and stable hand 0.4. So the decision matrix concludes that the stable hand surpasses all the rating except for design and safety. The stable hands score higher than our competitors.
Okay, so basically the whole impact of this project, the first and foremost part of this is pretty much the price. So in comparison to competition, the competition themselves are more costly when it comes to these products. So we also want to make sure that there's a seamless setup and interaction between the end user and the project, because some we see that the audience of some of these that they are they could be older, and as a result, that also comes with difficulty with using such technology. And one of the most integral aspects of this project is the modularity of it. Basically, it like pretty much add things on your own, and that pretty much brings on to the actual minimal waste and ability to repair. We're gonna make sure that we have like abilities to put in like pin headers so that it's really easy to take out components and put them back in, so that the user would not have to like get some special equipment or even have some soldering experience in order to repair the product.
So this is a quick breakdown of our needs identification and obviously what we want to have with our project. Obviously, we want to have an efficient operating system, good practicality and durability. And when comparing it to our two competitors, we would realize that uh, at our main end stage that we would have a better product than Gyro Glove, but compared to Steady One, it would still fall off to some extent. So for our system requirements, we have our marketing requirements as well as our engineering requirements. So our marketing requirements consist of an easy to use interface, lightweight and comfortable, power sufficient, fast responsivity, durable, a concealed design, and the motors must react according to the gyroscope motion tracking in real time. There's also a quick breakdown of our engineering requirements and justifications to the right. Uh, Basically, we're just focusing on how fast our project should respond in real time according to both the motors and the gyroscope, as well as being uh, a level of accessible to everyone of all age groups, because we need to consider the general market as to what our project is pertaining to. This is a quick down of the engineering, marketing, and trade-off matrix. So like I said in the previous slide, we want to make sure that we have something that pertains to everyone of all age groups and have it, be easily accessible and yeah, easy to use for people. So this is one of our mockups for our 3D models for what our project should look like towards the end. So right now it has two microservos and which will function as motors. And we have the microcontroller as well as the gyroscope underneath the hand and an LCD screen that will provide any kind of feedback towards the user. Anika, you're muted.
Okay, so basically for the things that we're being used, so we're going to be using three different things. This is what we're currently using. Of course, it'll be expanded more in the following semester. So what we've been using right now is pretty much using like a random number generation um, to basically utilize noise for it. Otherwise, we'll get like static and the same value, which is something that we don't want for this. We're also going to be using time series analysis. So basically using and training these moving average models. And this will be pretty much be used for data processing. And we're also going to be using other forecasting like methods. So basically using machine learning on top of that. And basically it's everything's going to be used to predict future data and predict future events. Because this isn't just like just a stabilization tool, it's also like a actual like a assistance device to actually show you how how well you're performing. This will pretty much be used to show if like someone's condition is getting better or even worse.
So this is a quick behavior module as to how our system should work. Obviously, the microcontroller is responsible for both writing the files in order to log results, displaying the results, as well as the motors responding to the gyroscope. And obviously, the gyroscope sensor is uh, connected to the microcontroller as to what functions that they should do.
So this is the function, this is the composition. So we have the microcontroller, the hub of the project. It is what processes the data. We also have the gyroscope, which is the main sensor that is used to collect the data. This is fed into the microcontroller, which is used to process the data. The feedback is going to be the visual or sensory feedback to this user to show the status of the device. We also have the writing data. We write the data received from the gyroscope to a file. This will be used to debug or to get additional information of the tremors. Also, finally, we have the motors. Based on the process data, motors are adjusted to fulfill the main purpose of the product.
All right, so basically, so this is our pretty much main project. I also have it in front of me. So basically, it's going to be utilizing a Adafruit Feather M0, and basically this is like the heart of the entire project. So also keep in mind that this is also like a prototype. Eventually, we'll also have this assembled and add additional components such as the LCD display. And basically, what you see here is that you have a actual microcontroller on the left, while we have the gyroscope sensor on the right. I think it's probably easier if I show it on my desk here. So basically, over here we have the gyroscope sensor, the microcontroller, and the servos that are connected to the PWM signals of the microcontroller, as well as the SD card attachment, which is integrated within the actual microcontroller themselves. So pretty much for the software. So first, there's actually two components to the software. So the first part being part of the actual microcontroller. So in the microcontroller, basically with these different components, there are different data types associated with them, and there's pretty much different ways of how these components handle data. So pretty much the actual Arduino code, um, we made a bunch of conversions within some of these initial variables to ensure that they're all like readable within all these different components. And it also has like initialization features that resets the servo's positions every time it's powered on. So this is one difficulty that we have faced, where let's say someone like immediately plugs the servos out and we plug it back in, the servos wouldn't reset position. So there was a contingency plan made for that. And basically, um, it also generates some unique file names, and as mentioned prior, we're using RNG to actually with like a custom method to actually generate these names. As for the desktop application, the main purpose of it is pretty much interfacing with the data collected from the microcontroller, and it's pretty much the main like hub of what the user will like interact with when it comes to the computer. It will contain like a ability to generate graphs, show all these different models and how and the results of those. So I'll also demonstrate in this presentation these graphs. And currently, what we have right now is like a moving average model with more methods coming in the future. It's right now it's only command line based, but we have initial like code for like the actual UI of the project, which will be completed in the following semester. Yeah, so pretty much this is the same exact project. Basically, it's just to show that the actual microcontroller and the actual project is working conceptually. And here is the actual generated graph from that program I mentioned prior. This is all made the graphs itself are made programmatically, so it's not like it was chugged into Excel or any other program. This was using a library on Python, and as shown, this predicted like a few events based on the moving average model. And thanks to the used libraries, we're also like have the freedom to pretty much export the image and even manipulate the image even further from that. And as for the cost, our projected total is going to be less than 100, but we are able to squeeze it down just to 70. So pretty much the most expensive component is of course the microcontroller, and it also comes integrated with that SD card reader, with the pretty much most second expensive components being the actual JavaScript sensor. And from our experience, we did have a second JavaScript sensor come in because the first one that we received was defective. And pretty much the rest of the components are mostly like resistors and things to kind of either reduce the noise or pretty much to organize everything else.
Leandro.
Sorry. Our project schedule and no not go milestone work. So our project 40% milestone aligns with the first phase of our project. The following semester, we're going to focus on the user interface, the external power solution, the fabrication of the final PCB design, finalization of the software components, and implementation of additional algorithms and features, the 3D printing and any irrelevant materials, and also the final assembly of the product.
So as for our conclusion and future work, we believe that we fulfilled what we wanted to do for this semester, and that was mainly create a working proof of concept. Over the winter break, we plan to have implementations of additional algorithms and methods, and an initial start as to implementing the user interface from our desktop application, as well as start the 3D modeling for a lot of the 3D printing parts that we want to be able to do. And for the spring 2021 semester, we plan to bring those parts that we've 3D printed and actually start the assembly of our final project, as well as the final PCB fabrication, and basically complete all of our software components as well.
Okay, so pretty much to bring up some programming challenges. So basically, like I mentioned before, we had an issue with pretty much the actual like variable conversion. So extensive testing was done to implement as much of these as possible, given the time constraint. So we did implement a bunch of solutions for that, and we actually have um, we have the actual conversions working. Everything is able to communicate with each other. The database file is able to be created. Another difficulty we had was to ensure that data won't overwrite each other, as in like pretty much the microcontroller opening the same type of file once it reboots. So basically, we wanted to use like a timestamp to name like the file so it avoids that. But we also recognize that there's no like real-time clock with the microcontroller, so that actually made that part difficult. So we had to implement our own solution in order to actually have that random file name on there. And basically, we want to and then on top of that, we want to ensure that everything is like power within a singular power source within the microcontroller, which also kind of brings up some issues with how data is being transmitted without the whole thing, because when we were assembling the whole thing, we realized that there was some like unwanted noise with some of the components. So so when you look at the graphs generated by the microcontroller, you see that there's like some like fuzzy mess between like a small range. So this is something that we are trying to avoid, and this is actually something that we've fixed to a good extent, and this will also be improved upon. And that's pretty much it for the actual constraints and issues that we've had with the code so far. And as for the ethical issues, so considering this is a medical kind of assistance device. The primary audience is pretty much those with like a medical issue, with the hand tremors, or even for therapeutic reasons. So this pretty much does create some sort of liability issue where there can be, conflicts between the end user and the actual creators or the project, if by any chance the user has misused or it has malfunctioned as a result of their fault or our fault. And there's also bias towards individuals with pretty much ordinary hands. So the project as is designed specifically for those who have, like, fully developed hands. But because of the modularity of this, solutions are being worked on to, like, have like these things tailor made, so that it is also able to um, be used for these other individuals. And the last part is like is you could pretty much exploit this whole thing from like a physical level because of again, this is also, even though modularity, it's helping the end user, it's a double-edged sword where it pretty much also comes to perhaps harm the end user, where it's possible to exploit the actual project itself by pretty much putting your own components onto onto our PCB.
So this is just a quick breakdown as to what was complex engineering in our project. So from a hardware and electrical side, we had to work with, fast response time and independent X and Y functionality. And in future time, we will be doing some fabrication of 3D materials as well as fabrication of the PCBs for further use of the project, as well as we intend to have an external power with voltage regulation. And for software, it's creating different iterations of 3D models in order to visualize what our final project should look like, and as well as implementation of multiple algorithms, some file I and O functionality for integration into multiple devices, as well as compatibility with different operating systems. All right, thank you. Any questions, comments, concerns?
Any questions?